My name is Maviala. I'm from Thales company in France, and I will be presenting today what we are doing in the application of big data analytics technologies to cybersecurity, and especially focusing on the detection part, presenting a new algorithm that we built, which deals with large-scale anomaly detection. So the agenda is going to be quite simple. I'm going to take just 2 minutes, I think, to present you the lab, my lab. It's ecosystem, and now we are trying to innovate in the field of big data analytics. Then I'm going to go straight to the main subject, explaining what are the main challenges in cyber attack detection. And after that, explaining what we can bring, and especially what big data and big analytics technologies can bring to answer the specific needs that we have in cybersecurity. After that, I'll be presenting the first use case that we built something like a year and a half ago or 2 years ago, which deals with batch anomaly detection in pig. And then I will explain how we switch from batch anomaly detection to real-time anomaly detection in Spark, and I will conclude. So as I told you, 2 minutes first to introduce a bit the laboratory in which I'm working. It's called the Sentai Lab. It's basically the lab dedicated to big data, big analytics, and visual analytics technology inside the Thales group. Our goal is basically to build prototypes, advanced prototypes, that will transfer after that to Thales business line so that they can make product out of them. And in order to do so, we have very strong collaboration with academics world, especially 3 universities in France. The first 2, which are Paris 6 and the University of Lyon, in machine learning, and especially large-scale machine learning, and also on large graph processing. And the last one with the University of Bordeaux on visualization, visual analytics. But let's go to the main subject by starting with expressing what are the main challenge in the detection of cyber attacks. In order to do so, I've kind of like segmented the cyber attacks in 2, starting by the non-targeted one, which are what we can say general public. They are often not very complex. They are using very common attack patterns. So it's basically phishing or things like that. The thing is that, as I told you, they are not targeted. But hackers just hope that under, for example, 1 million people that this attack will reach, there will be some that will fall in the trap. On the contrary, you have very targeted attacks. And this is the type of attacks that we are trying to, on which we are trying to improve the detection capacity. And these targeted attacks are especially targeting large company or administration, and the goals are, for example, to steal data, to steal intellectual property, or to sabotage some industrial infrastructure, for example. And what are the main characteristics of this type of attacks are the following. So they are very customized. Basically, what hackers do is to start by what we call a recon phase. So they will trying to find what are the typical software or hardware installed on the given information system. And they will build from that customized attack patterns. But also, they are quite often made through very large period of time. When I say large period of time, it could be multiple months or even years, which makes them very difficult to track. Because all the hints are spread through massive data sets, usually logs or network information. And in order to detect those two types of attacks, we have usually a traditional approach, which are basically built on top of or using expert rules, what we call signatures. So they are basically attack patterns expressed in terms of rules. And the problem with that approach is that basically they will be able to detect an attack pattern that has been seen before. So they won't be effective to detect either a new attack pattern or a customized one. So that's a big problem to detect very targeted attacks, as I told you. Second problem is that they are often not sized to handle very massive information. So quite often they are limited to, for example, analyzing the last n millions, for example, of events occurring during the last day or last week. So they are unable to detect complex attacks on large period of time. So they are suited for general public attacks, but absolutely not to detect targeted ones. What we need is innovative tools to be able to detect attacks, basically unknown attacks, without relying on any attack patterns, without needing to inject some a priori information about the type of information, the type of attacks that we are interested in detecting. And we want to do that on large period of time, which can be multiple months or even multiple years. So that's actually quite a challenge. What about the data that we have to reach this goal? Basically, the data could be collected at multiple levels. It could be collected, or it could be data originated from an application, for example. It could be a mail application or something like that. But it also could be collected at the network, for example, from a router or from a firewall, or from a system, operating system, for example. So you have multiple types of data that you will need to integrate in order to build or to improve the detection capacity. So here is a simple example of type of data that we are studying, which has been extracted from a firewall. So it's basically just a simple connection between two machines, which are characterized by their IP address. And you have some information given the protocol, the date time, the duration of the session, etc. So those are basically the type of information that we are analyzing. And data are big data. There are two concrete ways of exploiting this data. It can be the exploitation of logs. In this case, you are in a batch analysis, in a posteriori analysis. And the data that you want to analyze are basically logs, which are very massive. It could be hundreds of terabytes of logs for a given information system. Or the data can be very dynamic. What we are going to do, and what we are doing, is basically to build components in order to be able to ingest network flows, for example, and to extract from the flows which are the anomalous events. So in this case, the information is highly dynamic. It could be multiple gigabytes or multiple or dozens of gigabytes per seconds of network flows. So I'm going to present you the first use case that we have, which deals with batch anomaly detection. Essentially, because Thales has an activity where we have a team called a rapid response team, which is called by Thales client, where one of the clients is under attack. So basically, they have information such as logs, and they want to be able to detect from those information which are the signs that could reflect the ongoing attacks. So this is the first use case that we have, batch anomaly detection. Most of the logs that we have are network logs. So basically what we want to achieve is to audit this log, to extract from this log which are the abnormal events. So logs are either usually from firewalls, but also it can be originated from proxy a lot. So typical internet connection, these people has browsed this kind of site, etc. So this is the kind of information that we have. And it's hundreds of billions of events that we have to analyze. And of course, this information, these events, are non-labeled. So you can't build a model, supervised model, to discriminate from the attacks to the non-attacks. So the objective, given this context and this data, is to be able to build an unsupervised anomaly detection algorithm that will take as an input these network logs and pinpoint which are the abnormal events in these logs. So what are the challenge that we faced when we launched these activities? We faced actually multiple challenges. The first one is basically coming from the fact that quite a lot of open source libraries, algorithm libraries such as Mahout, for example, or Spark mlib, are not dedicated to unsupervised anomaly detection. They are much more oriented toward supervised algorithm or recommendation or simple clustering algorithm, but you usually can't find any open source anomaly detection algorithm. So that's kind of a problem. That means that we will have to develop one from scratch, actually. Second constraint, second challenge comes from the fact that data is of course massive, but it's also highly dimensional. Highly dimensional because in the raw data, you have a lot of variables that can characterize a given event, but also what we do is basically to build some other statistical indicator that will improve the detection process. So usually the event that we take as an input can have up to 100 variables. So that's a constraint that we had to take into account. Of course, when we do anomaly detection, one of the main problems comes from the fact that it often raises some false positive. And in the domain of cybersecurity, this has to be reduced as much as possible. So keeping a very low false positive rate is something very, very important. And the last but not least is that the output of the algorithm must be as understandable as possible, meaning that if we raise an alert, the operator has to understand why the algorithm has raised an alert. It's not always the case when we perform detection, unsupervised anomaly detection, but in this case, from the comprehension of the alerts, the operator will initiate some mitigation action. So it's very important that he understand why the algorithm has raised the alerts. So in order to answer these very specific needs, we build a set of tools in PIG. We build actually a new anomaly detection algorithm in PIG, which aims at estimating basically what is the probability that the given event appear. So that's basically the goal of the algorithm. So it's a probabilistic approach. And it's based on a notion which is called a copula. I will elaborate more on that later. But if we look at the pipeline of treatments, so basically you at the left you have the raw events. The raw events are then spread or cut into variables, into n variables. At this stage, we can even reconstruct some other variables. I told you some other statistical indicators. On each of these variables, we'll basically compute the density of these variables. We'll assemblate all the densities using the copula. And at the end, what we have is basically a score for each event. And regarding that score, we have to perform another step, which is to establish or to compute a threshold, which will tell us basically if the event is if the score is lower than the given threshold, then it is an anomaly. Otherwise, it is not. So after getting to the implementation of the pipeline in Pig, I will just elaborate few seconds. I will not go into details, but just so that you understand what is basically the tools that we use. What is a copula? Copula is basically a function to express a multivariate cumulative distribution as a function of its marginal distribution. So if we look at the literal expression, so P, U1, U2, is a bivariate cumulative distribution. And it can be expressed as a function C, which is a copula, which takes as arguments F and G, which are the marginal distribution. So it's just a way to compute the density. That's all. And there are many ways to compute actually this density. The most known is basically the case where CUV equal U product V. It is the case when the variables are independent. But there are many other ways to compute that. And just to finish the few words on copula, we developed actually a new way to calculate this density using what we call the indetermination criteria. So we built another copula which show very good statistical results. So that's one of also the main contribution from the statistical point of view. That's all. No more mathematical equation. If I go to the implementation in Pig, so basically we built the algorithm as a Pig user-defined function. For those who are familiar with Pig, you can build your own component using user-defined function, and we use algebraic user-defined function, which means that we only see the events once. In one pass, we are able to calculate everything that is needed by the algorithm. And we built three UDF. The first one is to calculate the density per variable, first UDF. The second one is the estimation with the copula. And the last one is to estimate the threshold on the score on the density. Three UDF, and on top of that UDF, we built two simple scripts, one for learning the model, and one for applying the model. So if we just look at the script, it's actually very, very simple. For those who are familiar with Pig expression, it's very understandable. So if I go very quickly, I load the model, I load the data, in the first line, then I pass it. On that part, it's where I calculate all the marginal distribution, and I store the marginal distribution in a HDFS. It's as simple as that. So I used this RUDF. There are functions that we built in order to compute the estimation. And this is also an UDF in order to parse the incoming data. So this is the learning phase. And if I go to the testing phase, it's more or less the same. I load the data. For each event, I pass it. And then I use the UDF, which is defined there, which is the copula. And from that three line, I get a score for each event, and then I can calculate a threshold and filter according to the calculated threshold. So this is basically how we integrate the UDF within Pig scripts. Very simple, very understandable sentence. So we were very satisfied of this first implementation. It basically fits the needs that we had at that time. So basically to perform a posteriori anomaly detection. But then comes another needs coming from the business side and tell us, saying that on top of this architecture, we would also want to add some real-time processing capabilities. So how can we combine both batch and real-time capabilities while avoiding the burden, if possible, of coding the either the algorithm or the application twice, both in the batch layer or in the streaming layer. So the answer actually that we took comes from a design pattern which is called the Lambda Architecture. Actually, I will not go into detail on these patterns because I think there are quite a lot of presentation on that type of architecture, and there's one actually by my colleagues in 2 sessions. I think will express what type of technologies that we use to build this architecture, and especially why we use, for example, Spark instead of another technologies. Just in a few words, the idea of the Lambda architecture is basically to build an architecture for both batch and real-time needs. So you have basically two layers. The first one is batch layer, where basically you can have Pig technology or Hadoop technology, but you also have another layer which is here, which is the speed layer, which is traditionally built around technologies such as Storm or Apache Spark, things like that. And all the information, the processing done by those 2 layers are then pushed to a serving layer where we can query the information or visualize the information. I will not elaborate more than that on the Lambda architecture. I will just show you what is the technical stack that we use to build this architecture. So starting from the left side, we used Kafka for the messaging part. So what we have on the output of this part are streams of data. So it basically streams of network data. And then this data can be processed. I will not elaborate on the batch, but more or less focusing on the streaming part. This streaming data can be processed by Spark streaming with very, very nice integration between those 2 technologies. The results of the algorithm running on Spark streaming are then pushed to Elasticsearch. Again, very nice integration between Spark in general and Elasticsearch. And on top of Elasticsearch, we built some visualization components using Kibana, which is actually from the Elasticsearch Log/Kibana stack. And we customized Kibana to develop some innovative visualization. One of the key challenge comparing to many applications of the Lambda architecture is that the model that we built is actually not only running, if we need, on the batch layer, but it also running in real time in the speed layer, not only to score the events, but also to continuously learn and update the model. So this is also a challenge. So we moved all the code from Pig, to Spark. And for those who are familiar with Spark, for Pig, we built all the algorithm using Pig UDF. For Spark, we built everything using nice features from Spark, which are called accumulators. So we built the density estimation, the copula, and the threshold estimation using accumulators. And it's actually very easy to transfer the code from Pig to Spark, because the function that you have to implement are more or less the same. It's update function. You have an incoming event. How do you update your model? You have 2 instances of your model. How do you merge them? So that's basically the 2 functions that you have to implement, either when implementing a Pig UDF or a Spark accumulators. So very simple when you have a code from Pig to transfer it to Spark. What are the advantages of moving from Pig to Spark? First, that wasn't actually what we were searching for at first, but it reveals that even though our pipeline is not very iterative, we don't iterate on the same data on which Spark is very good at doing that. But even if we only see the data once, Spark is an order of magnitude faster than Pig. We basically divided the time by 2. It's also easier to share information between functions and between components. In the script, basically, at the end of the learning phase, the model has to be put in Pig to a HDFS. And then, at the testing phase, it has to be loaded using the distributed cache of Hadoop. It's not very convenient to exchange information between UDF in Pig. So that's a key advantage. And the last advantage, which may be the most important one, is basically that we achieve to have only one implementation that we can use either for a batch application or for real-time application. It's really the same implementation of the algorithm. What we have to develop for one application or the other are simply the connectors. How do you get the data? Is it loaded from HDFS or is it coming from a Kafka stream, for example? But the core algorithm is the same. One of the disadvantages is basically it can be a bit difficult in Spark because you don't have all the data typing and all the schema that you have in Pig when you import the data. It's not actually true now, especially in the last version of Spark, where you have a data frame, for example, where you can define some schema over your data set. But it can be a bit troublesome, and for that, Pig is very good. So if we look at the code in Spark streaming, it's actually very concise. Here you have all the code. It has some encapsulation, especially for the model part, but you have all the code for the application for the anomaly detection in Spark streaming. So it's actually very concise, like 10 lines in order to define all the operation. So if I just look at the line, here it's just a simple, I would say, parameter, initializing the context. Then I instantiate a model and a way to calculate a threshold. I get a stream from Kafka, getting the topic on which I put all the information. And using that function, I'm scoring the stream. And after that, I'm filtering the RDD, the data set, with the calculated threshold. And then I'm putting all the information to Elasticsearch. So it's very simple, very nice integration between Spark and Kafka on this side. You can really easily create some stream of information coming from Kafka. It's actually a bit nicer in the last version, because one of the main problems that we had when using Spark with Kafka is basically that when you wanted to ensure zero data loss on the previous version of Spark, you had to write logs on another file system, HDFS, for example. On the new version, so this function, basically, they erase one part in Spark called the receiver, which was in charge of connecting to the Kafka streams. And we are able to ensure absolutely zero data loss, even without writing information to external system. All the persistence and the replication are done by Kafka itself. So it's really easier to integrate like that. So I will conclude the presentation by saying that in cybersecurity, and especially in detection of cyber attacks, big data analytics has become essential. But not only in the detection phase, there are a couple of domains, couple of challenges or needs in which we also applied big data analytics. One would be, for example, investigation and forensics. It's quite linked actually to the detection, but in investigation, you have usually one a priori information, which can be an attack, for example, and you want to draw all the events that are related to this attack. So it's quite complementary. This one is much more batch-oriented than the detection. But we have also another domain on which we worked a lot, which is situational awareness. So basically, one of the problems we had, or operator had in cybersecurity, is that quite often they don't know exactly what is the architecture or the topology of the information system they are monitoring, or they have a view, but it's biased. So that's a big problem in cybersecurity, because every action that you take are actions that are taken given the known information or the known architecture. And that's a big problem. And for that, we worked on a component which is able to redraw the topology using the log information. I will show you a small video, if possible, illustrating that. So the information as an input is exactly the same. It's network logs, and we were able to redraw all the topology. The circle or the neighborhood that you see are basically subnets, and given the rebuilt topology, we're then able to provide the operators with multiple operation, especially filtering operation using temporal time or time period comparison, but also something very interesting is that we can integrate in that type of visualization the anomalies coming from the detector. So basically, it can be very useful, because we know that one of the most powerful fusion algorithm is basically the human eye. So if you are able to provide the operator with a very nice visualization, or not nice visualization, but very concrete visualization, you will be able visually to fuse the information, which can be alerts, for example, and to find very interesting patterns that you wouldn't have been able, for example, to find in an automatic fashion.
I have a question here. Was that Katana, the visualization?
It's actually made from a framework called Tulip. It's from our collaboration with the University of Bordeaux. Tulip is an open source framework dedicated to graph processing and graph visualization. So it's made from Tulip this time. So from the cybersecurity point of view, big data analytics becomes essential. From the computational or the processing point of view, Spark, especially Spark, greatly helps to leverage the power of big data when you have multiple needs, or when you have both real-time and batch-oriented application, especially because we manage to use or not to duplicate the code for batch and for streaming application. What is next in the cybersecurity domain, or in the application of big data analytics to cybersecurity, is basically to work on decision aid and support tool. Given the detection that are raised by the anomaly detector, we want to provide the operators with decision support tool, because quite often the information that is raised here is not sufficient to initiate any action. So you have to help the operator to understand the alerts and eventually to provide him with some action to mitigate eventually the ongoing attacks. So that's something very important and on which we are going to be working. So I think it's my last slide. So thank you for your attention. And if you have any question, I will be happy to answer them. Thank you. Yeah. Yeah.
Oh, hi. Sorry, 2 short questions. Thank you for a good presentation. The first question is, what was the decision process to arrive at the creating the algorithms? Do you work with in-house teams of developers, data scientists, or do you work with an external partner or university? The second question, sorry if I may, is just around the the quantity of data, and how did you arrive at a policy of data storage and data policy? What was the policy to guide you? Would you need to keep 1 month, 6 months, 1 year, and things like that? Thank you.
Yeah, two interesting questions. The first one regarding how we built the models. We are a team of about 20 people, and in that team there are many profiles, including data scientists. So for that part, for the construction of the anomaly detection algorithm, actually we built everything by ourselves, from the theoretical point of view to the implementation, either in Pig or in Spark. For the log storage and policy of storage, it's actually quite funny because in France, I don't know if it's the same in other countries, but we have a law which tells companies that they have to store logs, for example, for a period of 1 year. But quite often they don't use this information with an objective of detecting, for example, anomalies or attacks that have been missed by other components. So this information is stored for historical reason or for legal reason. So we just upload it to our architecture and analyze it. So basically what we have is one year of data. Yeah.
Do you have any specials related to?
Can you please just repeat? Thank you.
Do you have any specials related to deployment model of your Spark applications, which is intended for fraud detections and stream processing? What is the deployment model of this?
For now, the deployment is mainly based on Yarn, meaning that we have a cluster which is basically dedicated for batch and for real-time application, and all the resources are monitored or are allocated by Yarn. But it's not actually the deployment that we will use in every condition, because in some other condition they may not need, for example, a posteriori information analysis, and this time we may not use Yarn, for example, to deploy Spark cluster, which can be deployed on its own.
So you're thinking about single dedicated cluster.
Yeah.
But here now it's Yarn server or Yarn client?
It's Yarn server, but the difference between these two are not really, I would say, fundamental between Yarn client and Yarn server. The main difference comes from the fact that the driver for Spark is not executed on the same computer or at the same place, whether you use the Yarn client or Yarn cluster. But the processing tasks are executed in the worker, and the more computer-intensive tasks are executed in the worker. So we can either use the Yarn client or the Yarn cluster. That won't make a big deal, actually. But it's actually, one thing that can be interesting is that using Yarn cluster, basically the integration with Elasticsearch especially can be more interesting, especially when you have an Elasticsearch server which is installed on the same cluster.
What makes you change to standalone server?
To standalone server?
To standalone cluster for Yarn, for Spark.
With
What forces you to change this decision?
Nothing. As I told you, we are an innovative labs, so we are not concerned a lot for now on the deployment phase. So we have our own cluster on which we install the application like that, but on the production side of view, it may not be deployed as I told you. Just that we have a cluster, and we have to optimize all the resource that we have in order to build those either scenarios or proof of concept. Yep.
I have two questions. Thanks for this great talk. The first question is about how did you go from a categorical variable to a continuous one?
Yeah.
Because we know that a couple of talks in a continuous variable. And the second question is about how do you build a decision function based on a coupler?
Okay. Two interesting questions. First one, regarding the copula, the answer would be that copula are more or less dedicated to, at first, quantitative variables. When you are using and when you are analyzing quantitative variables, you are sure that the solution, the copula, that will enables you to mix multiple distribution function, this copula is unique. When the variables are not quantitative, or when they become discrete, you still have a solution which can be acceptable, but you have no guarantee on the unicity of the solution. But basically, given the test that we did and the search that we did on a theoretical point of view, it's still interesting to work like that, especially because, as I told you, we can have up to multiple hundreds of variables, and it's very difficult to estimate density, or it can be a bit tricky to estimate a density in such large dimensional space. So one of the ways to deal with that is to use the copula to split all the computation variable per variable, and then reassemble the computation. So it's more efficient. That's what we found. It's more efficient to do it like that, even though the solution is not unique in this case. And the other question was, I don't remember. Yeah, okay. Basically, the copula, what it gives you, or what it enables you to express, is the cumulative distribution function. But the cumulative distribution function is just an integral over the density function. So what I showed you basically in this step, I think it was a bit before here, this is a cumulative distribution function, but I could have written exactly the same thing, but as a density this time. And what we use is not exactly this formula, but it's the density equivalence. So at the end, for what we have for each event is not exactly the probability, but it's the density of the given events. And then, given the density, we calculate a threshold, which tell us that if the density is lower than a given threshold, then we can flag it as an anomaly. So it's the copula. With the copula, we calculate the density, and on that density, we calculate a threshold. Exactly. And if the way actually to calculate the threshold, I didn't have time actually to speak about that, but there are multiple ways to calculate the threshold, and one of the way is exactly to look at the distribution of the tail using extreme value distribution, and that's what we do. Yeah.
Hi, I will have the evil question for anomaly detectors. How do you validate your results?
Yeah, that's a very good question that I will separate in two. From the theoretical or the statistical point of view, we validate the algorithm using traditional data sets. They are not very good, actually. I would say that they can be quite bad. But it's very difficult to validate and to find very good data sets, especially in cybersecurity, to validate algorithms. So there are multiple data sets. They are often quite old, but from a theoretical point of view, that's what we use. From an operational point of view, we also have a bunch of experts that will test, especially the detection capacity of the algorithm. We, for example, have a team of hackers. We call them ethical hackers. So basically, they will try to simulate multiple attack scenarios in order to validate the performance of the approach. It's not exhaustive. It's very difficult, actually, to validate, especially in cybersecurity, the performance in an exhaustive way. But that's basically what we do. Label data set from the statistical point of view, but also from the operational point of view, using experts.
Okay, thank you.
Hi, I have a question regarding the application in a real system, for example. Is the method robust to maybe a new application being deployed in an information system with will all the flags go red because there is a new pattern that you haven't discovered before?
That's a good question. And that's actually linked to one of the points that I mentioned. Quite often when people are using the Lambda architecture, they're only performing the learning phase in the batch layer. And that's something that is not possible in our domain, because basically when you deploy a new computer or a new application, you want your model to be aware of that deployment as soon as possible. And that's exactly why all of the learning phase is in the speed layer, meaning that the model continuously updates itself. As you said, if there is a new application, the model will raise an alert regarding that application, but it will also learn the pattern, and over time it will integrate this new application. Okay, so I think that was the last question. Thank you very much for your attention.